Assalamualaikum everyone. Welcome to my video tutorial for physics students. In this episode, I am going to talk about current, density, and drift velocity. How are these concepts related to electric current? To find out, just stick around, watch, and learn. The question is, an 18 gauge copper wire, the one usually used for lamp cords, has a diameter equal to 1.02 millimeters. This wire carries a constant current of 1.67 amperes to a 200 watts lamp. The density of free electrons is 8.5 raised to the 28 power electrons per cubic meter. Question is, find the magnitudes of letter A, the current density, and letter B, the magnitude of the drift velocity, and question letter C, by how much will the drift velocity change if the wire gauge is replaced by a 12 gauge wire whose diameter is twice that of an 18 gauge wire. First thing first, let's identify the given data in the problem. For the gauge 18 wire, its diameter, capital D, is equal to 1.02 millimeters or 1.02 times 10 to the negative 3 meters. We also have the current in the wire equal to 1.67 amperes. Likewise, we are given the density of free electrons denoted by small letter n equal to 8.5 raised to the 28 power electrons per meter cube. And we know that the charge of an electron Q has a magnitude 1.60 times 10 to the negative 19 coulomb. And our target variables are letter A. We are going to look for the current density denoted by capital J. Letter B. We are to calculate for the drift velocity denoted by V sub D. Alright, this is the drift velocity for the gauge 18 wire. And lastly, for letter C, we are to determine the new drift velocity V sub D when the wire is replaced by a gauge 12 wire. And it is stated in the problem that the gauge 12 wire has twice the diameter of the gauge 18 wire. Before calculating for the current density, let's compute first for the cross-sectional area of the 18 gauge wire. Alright, so using the formula for the cross-sectional area, which is the product of pi and the square of the radius, that is pi multiplied by 5.10 times 10 to the negative 4 meters, alright, quantity squared. Alright, so using your scientific calculator, we find that the area, cross-sectional area of the wire is equal to 8.17 raised to the negative 7 power meters squared. And moving on to our calculation for the current density, denoted by capital J, alright, it is simply equal to the amount of current I divided by the cross-sectional area, capital A. Or, substituting the quantities, we have I 1.67 amperes divided by 8.17 raised to the negative 7 power meters squared. Or, the current density, capital J, has a magnitude equal to 2.04 raised to the 6 power ampere per meter squared. It should be noted that the current density is not the same as current per se. Alright? If the current through a given circuit is constant, the current density at a given point in the wire, alright, may vary depending on the thickness of the wire at that point in the circuit. For example, in this diagram, the current through the given circuit, alright, may be constant or the same at any given point in the circuit, whether it is in the wire, alright, in the battery, or even in the filament of the bulb. We say that the current is constant. But the current density, however, is less through the battery when compared to the current density at a certain point in the wire. Alright? And this is because the cross-sectional area of the battery is larger compared to the cross-sectional area of the wire. Alright? So, we emphasize that the current density, capital J, is the current per unit cross-sectional area. Unlike current, okay, current density is a vector quantity that describes the amount of charges and the direction of flow of the charges at a certain point. Calculating for the drift velocity based of d, which is equal to the amount of the current density, capital J, divided by small letter n, which is the density of the free electrons, all right, multiplied by the absolute value or the magnitude of the charge of an electron. All right. So, we say that the drift velocity is just equal to 2.04 raised to the 6 power ampere per meter squared. All right. But we have replaced the unit ampere to coulomb per second. All right. So, in short, the current density is now expressed in coulomb per second meter squared. And that will be divided by the value of n, or the density of the free electrons, all right, equal to 8.5 raised to the 28th power per meter cube, all right? That's supposedly uh, 8.5 raised to the 28th power electrons per meter cube, right? So that small letter n still has to be multiplied by the magnitude of the charge of an electron, equal to 1.60 raised to the negative 19 power coulomb, okay, per electron, that is. All right, so if we do our math, we will get the magnitude of the drift velocity equal to 1.5 raised to the negative 4 power meter per second. As expected, the unit is in meter per second because in our preceding uh, equation or substitution, the quantities, all right, the unit coulomb gets cancelled, all right, and uh, the meter squared also gets cancelled. So what is left will just be the unit for velocity in the SI system, that is, which is meter per second. Right. Now this implies, all right, or converting it first to millimeter per second, so we get this drift velocity equal to 0.15, all right, in two significant figures, 0.15 millimeter per second. Now what does this imply? It implies that at this speed, all right, at this calculated um, drift velocity, we say that an electron would require 6,700 seconds, all right, which is almost 2 hours to travel 1 meter along the wire, right? May I repeat that again, once again? This drift velocity means that an electron would require 6,700 seconds, or almost 2 hours, to travel a distance of 1 meter along the wire. All right? Moreover, the speeds of random motion of the electrons are roughly 10 meters per second. That is around 100 times the drift speed that we calculated here. So, once again, to emphasize, we say that the current density, capital J, is proportional to the concentration of moving charged particles, denoted by small letter n, all right? Proportional also to the charge per particle, Q, and proportional to the drift speed of the particles, V sub d. Finally, we're going to answer question letter C, which is, by how much will the drift velocity change if the wire gauge is replaced by a 12 gauge wire whose diameter is twice that of an 18 gauge wire? We said that drift velocity equals current density, capital G, divided by the density of free electrons, which is to be multiplied by the magnitude or absolute value of the charge of an electron, right? And we also said that the current density, capital G, is just equal to the current, capital I, divided by the cross-sectional area, capital A, right? So we can express the new drift velocity, all right, in this expression. B sub D will now be equal to the current, capital I, divided by the cross-sectional area, which is 0.25 pi d squared, all right? But that is to be multiplied first by the product of N, which is the density of the free electrons, and the absolute value of the charge of an electron, Q. All right. Now, since only the diameter, the wire, has been changed or doubled to twice the original diameter, with all other quantities held constant, then we say that the new drift velocity, K, will just be quartered, meaning that 1/4 of the original drift velocity, 0.15 millimeters per second, is now decreased to 0.038 millimeters per second. All right? And we also say that the drift velocity is decreased, all right, the delta Vd from the original value of 0.15 millimeters per second to the new drift velocity 0.030 millimeters per second. We say that the delta Vd, or that the drift velocity, has been decreased, all right, by as much as 0.11 millimeters per second. The negative sign supports the fact that there is a decrease in the drift velocity. And this inverse relationship between the drift velocity and the cross-sectional area of the wire reminds us of the equation of continuity, all right, for an incompressible fluid, all right? The equation of continuity states that the flow speed of the fluid is also inversely proportional to the cross-sectional area of the pipe or the tube. So, that concludes my lecture for today. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page and please don't forget to subscribe to my YouTube channel.